So last time we studied how to determine if a precipitate forms, right, given the concentrations. We also did the cross product to figure out our products. So let me quickly give you a rundown of all of that. Okay, last time. So for example, AgNO3 plus BaCl2, right? Suppose these are your two reactants. I showed you how to cross I showed you how to cross multiply them to get never mind. Anyway, so they exchange partners. That's what we discussed, right? So suppose you were not given the products, you take this whole thing and you exchange products and you get AgCl and BaNO3. This is all old stuff from before. And how do I get this too? It's by doing the cross product. And then you look up your solubility table to figure out which one is the precipitate. That's what we figured out last time. Then we also figured out that things that are partially soluble, right, they can dissolve in very limited quantities, but not any further. So that's where Q versus K came in. If Q was less than K, then no precipitate forms. If Q was greater than K, then a precipitate does form. Right? Today, we're going to talk about what's called a common ion effect. And a common ion effect, if you look at it through the lens of the ICE table, looks actually very simple. And I'll show you what it means. I'll actually do two questions in parallel so you see the difference between a non-common ion question and a common ion question. So the first one is very simple. 0.5 molars of AgCl. Actually, hold on. AgCl has a KSP of 10 to the negative 8. Determine Ag plus concentration at equilibrium. All right, this you've done before. This is not common ion effect. You take your AgCl, which is a solid, you break it up into its pieces, Ag plus and Cl minus. ICE, solids don't go into the equilibrium expression. These are zeros, undissociated to begin with. And then you just do minus x, a standard ICE table, x and x. And so x squared is 10 to the negative 8. X is 10 to the negative 4, and you're done. That is the concentration of Ag plus at equilibrium. In a common ion effect question, you see how we start with zeros for the initial values? One of these initial values is not going to be 0. You're going to start with a pre-existing amount of one of the ions. And here's a question that deals with that. A solution contains 0.5 molars AgNO3. let's say it has 0.5 molars AgNO3 and some AgCl. I'm going to put a parentheses excess here. You don't need to worry about that. Technically, I need to put it there. AgCl. Determine the concentration or the molarity of Ag plus at equilibrium. Now, here's the analysis. AgCl needs an ice table because this only dissociates to a limited extent because it's sparingly soluble. Right. AgNO3, on the other hand, it's a different story. AgNO3 is a highly soluble compound. How do I know? Well, you can look up your solubility table. So AgNO3, before AgCl has any chance to dissociate, think of it like that, AgNO3 will completely break down. So 0.5 molars of the highly soluble AgNO3, before the other thing breaks down, think of it that way, breaks down into Ag plus and NO3 minus. And so this is 0.5, this is 0.5. So when we draw the ice table, oh, why did I put square brackets here? This should have just been Ag plus Cl minus. So Ag plus Cl minus. Don't care. But this time, this guy is going to be 0.5 because of the pre-existing Ag plus from AgNO3. Right? This is going to be 0 because the only source of chloride is AgCl, and AgCl hasn't dissociated yet. That's how we're imagining it to be. Then it's regular ice table, plus x, and so 0.5 plus x and x. And so when you set up the equilibrium thing, it's going to be 0.5 plus x times x equals 10 to the negative 8, right? We can use small x approximation here. That goes away. And so x is 10 to the negative 8 divided by 0.5. And that's it. One over 0.5 is 10 over 5, which is 2. So this is 2 times 10 to the negative 8. Yeah. Any questions? I'm sorry. I just realized I had my speakers turned down all the way. Was anybody saying anything? Can one of you say your name just so I know that my speakers are not on mute?
Natalie.
Thank you. Okay, so they're working. Great. So that's the common ion effect. You will be given two things, one highly soluble, one not so soluble. You take the highly soluble, you break it apart, and those values go into the initial of the ice table. That's the difference with a regular non-common ion question. Okay. Moving along. Let me just pull up your textbook so I see a rough breakdown of the topics. Did I cover everything? Did you guys do complex compounds? Because some professors do it, some don't. KF. Complex formation questions. Blah, blah, blah. Common ion. Yep, that's that. Anybody remember? Complex formation. Those things look like this. Let me show you. So for example, Fe H2O 6 2 plus.
I don't recall him. I don't remember if it was discussed in class, but I know it was an Alex topic. So I'm assuming it might be on the test, but I'm not entirely sure.
Yep. So complexes were on the test. Did you ever see a question on Alex where the ice table, it was an ice table question, and the K value, instead of being very small, was very large?
Yeah, that definitely was on Alex. I think it was the last topic.
Got it. Yep, makes sense that it is the last topic. All right. All right, we're on for a ride. And that will be the end of this chapter, complex formation. So you know that covalent compounds exist. You know that ionic compounds exist. There's a third class of compounds that are called complex compounds. So let's say this is complex equilibrium. Despite the name, there's nothing complex about it. It's just the name that stuck. Complex compounds are held together by what's called a coordinate bond. This is I guess, a new bond that you haven't seen before. Let me adjust this. Coordinate bond. And complex compounds are always kept in square brackets. Not to confuse the square brackets of molarity. So for example, AgH2O6 is a complex. Oh, sorry, let's put a plus there. That's a complex. But if you want to denote the molarity of this complex, then you put the molarity square brackets. So you'll have two copies of square brackets, and that's okay. But just keep in mind that complexes themselves have square brackets of their own. Square bracket, put the charge outside, and then external square brackets for molarity. So, right, there's two parts to a complex compound. There is the metal, right? And then there's the other stuff. The other stuff is called the ligand. So there's usually a metal and a ligand. And if all of your ligands are water, then the complex is called a hydrated complex. Hydrated complexes are important because that's how you can think of it as all complex reactions begin with a hydrated complex. And so here's a question. So there's two parts to this topic. The first is writing down complex formation reactions. And they're very simple. And the second part is to do with ice tables. And the only new thing about the complex ice tables is that your K value is really large. And so you'll need to do some math voodoo to make it really small. Okay. Writing complex formation reactions, they're very simple. So suppose a question says, write down the first step, last step. Let's say first step, just to give you a little more practice, I'll say first step, second step, and last step. Along with overall reaction in the formation of FeCN6 4 minus. Have you seen this in Alex or anything before? I remember when I did Alex, I had this going on. Okay. Oh, okay. So we're not okay. Because some professors do it, some don't. I had a class last semester where they didn't do it. Okay, so the idea is very simple. You start with a completely hydrated metal complex. So what's our metal here? We have an Fe, and our ligand is Cn minus. Cn minus is a polyatomic ion, and you know its charge because you've seen it before. Cyanide has a minus charge. Okay. If cyanide has a minus charge, we don't know what the charge on Fe is. Let's call it X. So set up the algebra. X plus you have 6 cyanide, so 6 -1 charges. And the charge on the whole thing is -4, which means that X is +2. So this is what you're dealing with. You have Fe2 plus, and you have cyanide minus ions. So break that up, figure out the individual charges like we did, and then start with a completely hydrated metal complex. So Fe, you've got 6 ligands in finally, right? That's the final stuff. So let's start with 6 water molecules. There. Now, the idea is very simple. Every step is replacing one water molecule with a ligand, one at a time, right? So there will be 6 steps because there's 6 ligands to replace. So let's start with one ligand that we replace. So what happens is one of the water molecule gets kicked out, so there's only 5 left. The cyanide takes its place, and the kicked out water molecule appears here. Now let's figure out their charges. This should have been a +2. Water is a neutral molecule, so +2. So the whole thing is +2, 2 plus. What about here? This is +2. This is all zeros, and this is -1. So that's 1 plus charge. And that is the first step. Okay. The second step is to take what is formed in the first step and replace it replace another water molecule with a ligand. So we've got FeH2O 5CN plus oh, by the way, I shouldn't mention that this thing has a minus charge. You never write the individual charges of the constituent parts of a complex. Just like when we write NaCl, we don't write Na plus Cl minus, right? No charges. Okay, replace this with another cyanide as usual. So we get FeH2O4. Another water molecule got kicked out. Now we've got two cyanides and water. Let's see, that's a 2 plus 0 and 2 times -1, which is neutral. So the whole thing has 0 charge. And that's the second step. So now we can do the third step, the fourth step, the fifth step, and so on. Each time starting with this guy. Now you tell me what the final step should be. Without writing down all the steps, what would the final step look like? We're throwing out one water molecule at a time, right? So by the time we get to the last step, how many water molecules will we need to throw out?
There'd be only one water molecule that you have to get rid of.
Exactly. So B, Fe, one water molecule left to be thrown out. We need a total of 6. So there already have been 5 cyanides. Exactly. Replace that with the last cyanide, and you get our finished product. The water molecule gets kicked out. It's all cyanides now, which is what we wanted. And that last water molecule kicked out appears here, and you're done. Charges, plus 2, 0, 5 times -1. So that's 3 minus. And this one plus 2, 6 times -1, 4 minus. And that's it. The idea is very simple. Start with hydrated and replace one at a time. That's all it is. Oh, and also keep track of charges. Once you know the charges of your individual components, it's all about combining them. Okay, any questions? No, this virtual setting is throwing me off a little bit because I'm used to like looking at all of you in the eye and like immediately getting a gauge on if you feel confused or not. And so like I don't have that suddenly. And so my brain is like, wait, what? Is it clear? Is it not? Anyway. Okay. Moving along from this. My OneNote is acting up. Let me restart it. Okay. Now let's do some ice table questions with this. Yes. Um, Fe FeCl2 and NaCN are combined in a solution with molarity. So I'm giving you the combined solution molarities. If you don't have it, then you know what you should do, millimoles. With molarities 0.5 and let's say 0.3. And 0.35. Calculate the molarity of Fe2 plus at equilibrium. Oh, I forgot. In the last question, what is the overall reaction? The overall reaction is very simple. You do it all at once. You start with all hydrated, which is 2 plus. You've got 6 water molecules. You want to replace them with 6 cyanides, so that all the water molecules get kicked out. Like so. And so this is the overall. Oh, 6 water molecules. And there should be a 6 there. Overall, you simply get by adding up all the individual reactions, and this is what you would get. Pretty sensible. Okay, on to this question. FeCl2 and NaCN are combined in a solution, polarities, blah, blah, blah. Calculate Fe2 plus at equilibrium. This is basically a complex formation sort of question. And I'll also give you the Kf of FeCN6 4 minus is 10 to the 8. See, really large value instead of really small values. That's a complication. We can't do small x approximation. So let's see how to do this. So our complex of interest here is this guy, right? Let's just blindly go ahead and write down its formation reaction. So we're going to eventually form FeCN6 4 minus, which means it started out with all waters, 6 of them. And we had 6 cyanides put in, and then you get 6 water molecules put out. ICE, ice table, don't care about the water. And now we just fill in the information. This thing has a K value of 10 to the positive 8. Okay. Now, what is the concentration of the hydrated iron, FeH2O6? Here's something to note. The concentration of the metal and the concentration of the hydrated metal is always the same, because all of the metal in solution already exists in the hydrated form. If you dissolve a metal, it will immediately turn into its hydrated form. So this thing here is simply saying, what is the Fe2 plus concentration? Cool. Fe2 plus, the source of that is FeCl2. This completely breaks down into Fe2 plus and 2Cl minus. 0.3 becomes 0.3 and 0.6, but we're interested in this guy. So that's a 0.3. Cyanide, we said, and sodium cyanide has a molarity of 0.35. So that breaks down into Na plus and Cn minus. So 0.35, 0.35. And so that is 0.35. And no complex has formed in the beginning. That's a 0. If you just go ahead and set up your ice table this way with X's and stuff, you won't be able to solve this question, because the K value is really large and you have big coefficients like 6. So this is a 6th power equation. Too hard. So here's what you do instead. Step 1, you'll have 2 ice tables. The first one will be a fake one. The second one will be the real one. In the first ice table, you react to completion. We've done this before in titration. Which one is limiting here? Oh, there's coefficients involved, so it's not so straightforward. Okay, so let's do by trial and error. Let's say all of this guy gets used up because it's limiting, right? Let me start by writing out the x's just for reference. This should have been a minus x. This should have been a minus 6x. This should have been a plus x. Okay, so let's suppose that all of this gets consumed, negative 0.3. And so if I say that that's negative 0.3, this has got to be 6 times as much. Negative 6 times 0.3. Can you see that this will come out to be a negative value when I add it up? 0.35 minus 6 times 0.3. So I'm looking at the wrong limiting reactant. So it must have been this guy. Let's say that all of this gets consumed. So minus 6x is minus 0.35, which means x is a 1/6 of that. Let me use my calculator. 0.35 divided by 6. .0.058. That's okay. That will not result in a negative value. So it seems like we've chosen the right limiting reactant. Let me calculate the difference. 0.3 minus 0.058. So that's 0.242. This is 0, and this is plus x, so plus 0.35, which is 0.35. Great, we have reacted this to completion. That's step 1. Step 2 of the ice table is pretty straightforward. Flip, and that's your new ice table. So reactants become products, product become reactants. Oh, I see. There was a question. My Zoom is also acting up. I don't know why. Feel free to unmute yourself and ask me a question, just like you do in class. That way I don't miss them. How do we know when we react to completion or not from the question itself? You always react to completion if the question is about complex formation. Another hint is your K value will be very large. What the strategy here is to convert a question where the K value is really large to a question where the K value is really small. And an essential first step is to react to completion.
I have another question. So when
Yep.
we do titrations, we also react to completion, but the X value is not large. So when it's a titration problem, we react to completion. And then also when the X value is large, we also do the same, right?
Yes, correct.
Got it. Thank you.
So yes.
Sorry, I have another question. Under the complex ion, it's plus 0.35. Isn't it supposed to be plus 0.58, or am I wrong? because it's plus X.
You're right. You're right. I'm sorry.
Okay. All right, thank you.
This is a plus X, not a plus 6X. Thank you. Plus X. X is 0.058. Yeah, so this should be 0.058. I put in plus 6X for, yeah, by mistake. Thank you. Okay, now flip. Products become reactants. So we've got FeCN 6 4 minus plus 6 H2O, useless for an ice table, comes FeH2O 6 2 plus 6 cyanide ions, and ICE. Make sure to flip your values. Cyanide was 0. No, cyanide was 0.058. This is something, this is 0.242. So nothing crazy has happened so far. We just reacted to completion, flipped it, and a new ice table. This is the flipped equation. So what will be the K value here? What happens when you flip an equation to the K value?
One over K.
1 over K, the K becomes reciprocal. K also flips. So this is 1 over 10 to the 8, which is 10 to the negative 8. Nice, small value. That's what we wanted. Okay, so minus X, this is a true ice table. Minus X, plus X, plus 6X, 0.058 minus X, 0.242 plus X, and 6X. Oh man, why does this keep happening? Anyway, so let's set up the algebra. 0.242 plus X to the power of 1, 6X to the power of 6, and 0.058 minus X to the power of 1 equals 10 to the negative 8. Fantastic. So now I can go ahead and do the small x approximation. And so solving for 6x to the 6th power, I get 10 to the negative 8 times 0.058 divided by 0.242. Now, how do I isolate my x? You tell me. So x is trapped in a 6th power at the moment. How do I untrap it? If x was trapped in a square, I would square root it. If it's trapped in a 6th power, what do I do?
6th root.
Exactly. So you take the 6th root of both sides. And that goes away. And so x divide both sides by 6. It's a 6th of the 6th root of 10 to the negative 8 times 0.058 over 0.242. And that's it. But the question said, what is the concentration of Fe2 plus at equilibrium? Fe2 plus is the same as Fe with water. So it's that. So when you solve for x, you got to add it to 0.242 to tell them what the answer is. Okay. Any questions? So that concludes this chapter, I think. Okay, I think it's safe to move on to this. What was this graphing stuff that you wanted me to go over? You said it's on Alex on Blackboard. I think I do have access to Blackboard. Let me see if I can find it. This is 2022. Right. 20. Fall, Gen Chem 2, 104, R1. Yeah, this is you guys. Okay. Now, where's this graph stuff that I shouldn't be looking at?
I think it was on the 2013 exam. He posted it's all the way on the bottom.
Okay, 2013, I see. This thing has the graph that he was talking about?
I think it was the last problem. I'm not sure who asked the question, but there was a graph on the last question.
I think it was review part 2, the
Re-
first one.
Review part 2. Okay, I'll go over both. Review part 2, first one. And where's the graph? Oh, this thing.
Yeah.
I see. Oh, so he's doing a full-on buffer stuff. Let's see. I see. Those are just easy values, A, B, C, blah, blah, blah. Okay. Okay. All right. In the case of buffer questions, you have this question where what's the buffer range? So if it's a acid and conjugate buffer, remember a buffer is a weak stuff plus its salt plus its conjugate. So if it's acid conjugate, then the buffer range is pH plus or minus 1. Sorry, pKa plus or minus 1. And if it's base with its conjugate, then it's hold on. The buffer range, the pH buffer range is pKa plus or minus 1. And in the base conjugate case, it's POH equals pKb plus or minus 1. So basically, if you don't stray away too far from the pKa value, then you're still in a good range. That's all it's saying. Okay, and the graph of a buffer always remains the same. It's this thing, how the pH of a solution changes and so on and so forth, volume of acid added. So you can have based on whether you're dealing with acid and conjugate. So this is acid conjugate graph. So your buffer is made of acid and conjugate. To acid conjugate graph, you add base. So this is like volume of base added. And then the y-axis, so everything is basic here. The y-axis becomes pH. Sorry, pH. Volume of base added. So actually it should be pOH. I think. Let's see. pH is in the case of a thing. Weak acid with a strong base. Oh, I see. Okay. So with an acid conjugate buffer, you're adding base. And so if you do a pH graph, this is what it looks like. Initially, the pH goes up a lot, and then it sort of flattens out. And then it increases drastically again. And then it flattens out sort of at the high values. So it's like that kind of a thing. This flat region is the buffer region. Let me make that not that flat because it needs to be a little, it's fine. So these pH values that you're looking at, this is pKb, pKa -1, and pKa +1. So this is the graph for an acid conjugate buffer to which you're adding a base. On the other hand, if you have a base conjugate buffer, and you're disturbing the buffer by adding acid, then this is what happens. Now, volume of acid added. Once again, we have pH. Adding acid decreases the pH, right? So it starts up here somewhere. Then it sharply drops. And then flattens out for a little bit. Oh, sorry. It drops sharply. And then it sort of flattens out a little bit. And then it drops sharply again before flattening out a second time. So this is the usual thing. Sharp drop, flatten out, sharp drop, flatten out. In the case when you're adding a base, then it's going up because adding base means you're making the solution more and more basic. If you're adding acid, then the graph goes down because that's low pH and so on. Once again, this is If you want pH on the x-axis, then this is still pKa plus 1 and pKa minus 1. Why? Because you'll use POH, you'll calculate your POH using this, but then you'll convert your POH to pH by doing 14 minus. That's the same as starting with pH equals pKa plus or minus 1. Does that make sense? 2013 practice exam. Yeah, I'll go over that. So you should be given the pKa or the pKb value in the question. Add 1 to it, subtract 1 to it. That's how you get the range. The beginning and the end of this first plateau, that's your buffer range. Another situation where the graph is applicable is, so this is strong stuff that's being added each time. So if you're titrating, you can think of this also as a titration curve. This is the titration between a weak acid and a strong base, and this is weak base plus strong acid. Okay. Does this make more sense, or are you still confused? Okay. Good to see a thumbs up. All right, I think that's what it is. And yeah. Let's move on from this on to, you said there was a copy of this on 2013 practice exam. Let's see. Oh, nice. What do we have here? We're adding HNO2 and NaOH. This is a weak acid, strong base. You're given the Ka value, take its pKa. And this time we're adding a base, so the graph will go down. Sharp drop, plateau, sharp drop, plateau. That's the one. Calculate your exact pKa by taking negative log. Add +1 and -1. Mark the first plateau like that, and you're done. Okay, so that's easy. Okay. I did receive some emails regarding something on the test that supposedly was difficult. Keep in mind, we also have, you know, a review session coming up on Thursday. I know it's just on the same day as your exam, but we'll have time. I think Nope. All right, by request, let's do this. Chem 104, exam 2. So maybe we can do this. We can do one of these today and one of these on Thursday. So one of these, I think he went in class over. Which one is it? 2013 or 2014?
He went over 2014, so I think 2013 is the one that's left.
Cool. Cool. Let's start all the way at the end. This you know how to do. I'm gonna go over question 7 and 6, and then go over everything else in class, so that I have something to cover in class. You know what? Let's just do this whole thing, because who cares? Yeah, I want you guys to have the time to do all of this. Yep. Okay. I saw the heart reply. Thank you. My pleasure. Okay. Insert, print out. Okay. Let's see. And let's start with the last one. Okay. Draw the titration curve, blah, blah, blah. We'll do that later on. Using a 1.2 molar NaOH aqueous solution. Label the points at the following places. Initial pH of the 0.15 molar HNO2 aqueous solution, 1 milliliter added base, half equivalence point, and excess base. All right, sure. So I'm gonna draw a rough sketch and then we'll mark the points later on. So we start with some kind of a pH, sharp drop, plateau, sharp drop, plateau. And we can immediately start by marking these two. Oh, come on. I have no idea why this keeps happening. Ugh, so annoying. Okay. Yeah, and so this is pKa +1 and pKa -1. Okay. First thing that they want to do is we want to mark the initial pH of 0.15 molar HNO2, which means they want the value here. This would be the initial pH of the HNO2 with no base added. Okay, so that's a very simple calculating the pH of a weak base sort of question. React this with water. This is a base, so it's going to absorb H plus, HNO2 plus, sorry, H2NO2 plus OH minus. No, HNO2 is an acid, I'm sorry. Oh. So I'm doing this wrong. We're adding a base, right? So the thing should be going up because bases have high pH. So we're going to start somewhere. We're going to go rapidly up, plateau, rapidly up, plateau. pKa -1, pKa +1. We want to mark this first point. Only acid, no base added. Okay, so going back to HNO2, HNO2 is a weak acid. Let me mark that. So it's going to break down, it's going to react with water to break down into into NO2 minus its conjugate plus, what is it? H3O plus ICE. This is so this is HNO2 alone, right? So I can use the 0.15. Don't care, 0, 0. Minus X plus X plus X. And so 0.15 minus X, X, and X. And so X squared over 0.15 minus X equals Ka is what I need here. 7.2, 10 to the negative 4. That's on the cusp of being like either small enough for small x approximation or not. Let's just go ahead with small x approximation. And so X is 7.4 times 10 to the negative 4 times 0.15 square root. If you do the 5% test, I think it will check out. So this comes out to some number. Take that number and divide it by the 0.15 initial value times 100 and see if it's less than 5%. I think it will be. But great. So that's your thing. You're going to calculate the pH by taking the negative log of that. Let's see if I can do this on my phone. Or you know what? Let's use a Symbol Lab. Negative log of the square root of 7.4 times 10 to the negative 4.
I think it should be 7.2.
7 point, yeah, thank you. 10 to the negative 4 and 0.15. 1.98. Great. That's my initial value. So the first thing here is 1.98. Okay, next up is 1 milliliter of added base. Okay, no problem. This is titration now. HNO2 reacts with the strong base NaOH. Strong base, weak acid gives what is it? NaNO2. This comes from the broken pieces, and H2O. We're gonna do millimoles this time because volumes are changing. 100 times 0.15 is 15. 1 times 1.2, 1 milliliter times 1.2 is 1.2. 0 and 0. React this to completion because this is titration. Negative 1.2, negative 1.2, positive 1.2, positive 1.2. And so I get 14, 13.8, 0, 1.2, 1.2. Water, don't care. What do I have surviving at the end? I have a weak species. I have its conjugate, i.e. salt, and I have none of the strong. This is a buffered mixture. Henderson-Hasselbalch. pH equals pKa plus log conjugate divided by acid. pKa, what's the negative log of this guy? Let's figure that out. Negative log of just that. And no square root. 3.14 pi. Plus log millimoles of the conjugate, 1.2. Millimoles of acid, 13.8. So pi plus log of 1.2 divided by 13.8.
Wait, what happens if you had some base left?
Oh, then the base dominates. Remember
Mm.
the 3 cases of titration?
Right.
And then you forget about everything else and you just calculate the pH for the strong species.
Right.
2.07. Yeah. Great. So this is A, B, 1 milliliter of the base added. 2.07. So I guess somewhere over there. 1 milliliter of base added. Oh, our pK was 3.14, right? So this is now 4.14 and 2.14. So actually it's pretty close up here. 2.14. Yeah, this 1 milliliter stuff. Great. Come on. It's so annoying. Okay. 4.14 and 2.14. 3.14 plus 1 and minus 1. And this is where the 1 milliliter was. 2.07. Okay, great. C, half of the equivalence point, no problem. HNO2, NaOH, NaNO2, H2O. ICE, millimoles, 15. Don't care. Half of the equivalence point means do halvesies, so 7.5. Equivalence titration means put all of it, 15. 0, so once again, react to completion. So you got 7.5. Oh, there's a shortcut. I forgot to tell you guys. At the half equivalence point, things become nice. At the half equivalence point, the pH is always equal to pKa. Great, so we're done with C. pH is pKa, which is 3.14. Which is over here. .14. Volume of the base added. Let's see what the volume of the base added should be. You want to get, so you have 15 millimoles of HNO2. You want to get half of those millimoles as NaOH. Your NaOH, well, so let's see. You want 7.5. Your molarity is 1.2 molars. And so the question is, what is the volume? We'll solve for volume. 7.5 divided by 1.2. Gives you the volume. $6.25 milliliters. Lastly, equivalence point. That's easy. HNO2 plus NaOH gives NaNO2 and H2O, 15 millimoles. So we'll have to do all 15. Water don't care. 0, minus 15, minus 15, plus 15, 0, 0, and 15. Out of this, Na is useless. It's neutral. It came from a strong species. So we have 15 millimoles of NO2 minus. And we need to calculate the pH for that. What is the total volume that has been used up in this whole thing? HNO2 had a volume of 100 mils. Given in the question. NaOH, the volume isn't given, so we do the same game as before. We want 15 millimoles of NaOH. Its molarity is 1.2 times volume. And so volume is 15 divided by 1.2. It should just be the double of what we got last time, 6.25. So 1250 milliliters. So the total volume is 100 plus 1250, which is 112.50. And so the molarity of NO2 is going to be 15 millimoles divided by 112.50 milliliters. Which is, you know what? After this, let's save the rest of the material for review. Because that would be a good balance. Okay, so we have NO2 minus, the star of the show. This came from a strong weak acid, so this is basic. So it seems like it's going to be one of those except H plus kind of bases. There. This is now 0.13, water don't care, 0, 0. Okay, minus X plus X plus X. 0.13 minus X, X and X. And so X squared over 0.13 minus X should be equal to KB, because this is a base equation. We're not given KB, we're given KA. That's okay. KB is going to be 10 to the negative 14 divided by KA, 7.2 times 10 to the negative 4. Yeah, whatever that is, 10 to the negative 14 divided by 7.2 times 10 to the negative 4. Solve for X. And that tells you where the next pH is going to be at. I think it's going to be for here, if I'm not mistaken, or somewhere. But the volume of base added that also you calculated was what, 12.5? 12.5. And then the last question is excess base added 100 milliliters. This is the case in which the strong species will survive at the end. And so it will dominate. So the question becomes very easy. Let's end with that. So annoying. X is base. I'm gonna mess up with one of these ice tables because no, this one. I don't want to write all of this again. So that's 15. And NO2 minus NaNO2 water H2O. Excess base. Assume 100 milliliters of base is added. Okay. 100 times 1.2 is 120. Zero. So this time this is limiting. Minus 15 plus 15. So none of those weak species survives. 95 of the strong species survives and 15 of this survives. This dominates. We've got 95 millimoles of the strong stuff in how much total volume? We had 100 milliliters of HNO2 and 100 milliliters of base. So that's 200 milliliters. $95 over 200 should be approximately a half. I think it's exactly going to be 0.45. So what do we have? We have 0.45 molarity of NaOH. Well. NaOH breaks down into Na plus, OH minus, and it's a strong thing, so all of it breaks down. So this is going to be 0.45. And so POH is going to be the negative log of 0.45. And then do the 14 minus dance to figure out your pH. And that goes maybe over there. 100. So this is sort of like every titration question crammed into one. Along with writing it out on a graph. Okay. Any questions? All right. So here's what I propose. I'll do the rest of this in class, along with any additional questions that you have. Okay, great. I will process this recording and upload it. Oh, also, I'll send out an email, but the recording for last class is finally processed and available on YouTube. And I'll send out an email. Yep. All right. See you guys next week.
Thank you.
Problem.
Thanks.